All right. Hey, everybody, thank you so much for being here. It is always great to be amongst the concrete crazies here at American Concrete Institute. And it's great to see a lot of young folks in the audience, too. And there's a lot of interest in this. I'm going to be starting out thinking a massive thanks to a lot of these people listed down here at the bottom of the slide. I could not have done this work without them. They did a ton of testing, a ton of work, because it takes a lot of data to do machine learning well. All right. So a big thanks to FHWA for funding this work, Illinois DOT, NSF as well, and my cohorts on the FHWA project, Dr. Kim Curtis, Dr. Lisa Burris, and the amazing Cecil Jones. Again, thanks for all their help. And I also have to thank Kermit the Frog, and I'll explain why in a second, but Kermit the Frog will be a co-presenter with me in this presentation. So will AI and machine learning, will it change everything? I know when I'm teaching my undergraduate reinforced concrete class, there is some uneasiness amongst my students about AI and machine learning and what it's going to mean for them in the future. And maybe some of you feel some of that uneasiness now. Here's a very cool graph of OpenAI stuff from Chat GPT, and it's showing the progress from 3.5 to 4.0. And these are a lot of different tests that many of you in the room might have taken, like the GRE, like AP tests. And this is the percentage. This would be like 100% perfection. This would be it didn't do so well. And if you're a lawyer, ChatGPT is smoking the LSAT and it is smoking the bar exam. So it's doing really well. But for computational stuff, it's improving, but it's not doing as well, but it's improving and it's getting better all the time. And so how do I see AI and machine learning? And how do I think you should see AI and machine learning? And I think it's like a paintbrush. If you have to paint your house, you have to paint a painting, you have to paint whatever, are you going to want to paint with your fingers? Or do you want to use a tool like a paintbrush? And that's what AI and machine learning is. It's like a paintbrush. And like if I want to paint a painting, right? Oftentimes we would use a paintbrush, but my daughter, she uses her iPad to do all of her paintings, right? All of her drawings. And she looks at this and I look at this as like a tool, AI and machine learning. But DALL-E 2 is already doing this every day, and this is definitely AI machine learning. You type in what you want, a happy corgi, and look at that, it spits out. But just like art, you have to know what you're doing. You have to be trained. You have to see what's going on. Because when I run DALL-E 2, this is what I get. Okay? This is where I was trying to get some llamas in front of the Eiffel Tower, and it looks like they're carpets, and like, I didn't look at the Eiffel Tower. But anyway, my point to all of this is that this is an amazing tool. This did appear in 30 seconds, which is pretty awesome, but we need to know how to make these tools better. So really, if I had to tell you, if there's one takeaway, if you're a young person, you're working on machine learning, it's this slide. Okay, how are you going to create useful AI and machine learning tools? So it's easy to create tools. That's easy. Hit a button and you will get a tool. Okay, how do you make a useful one? And I think you need to ask a specific and reasonable question. That's number one. If you ask for everything, that's tough. If you ask a very specific and reasonable question, that's much easier. You are going to need lots of useful data, and you need to check the results and improve again and again and again. Now, a good machine learning model can be easily plus or minus 20% over an expected value. A good machine learning model can easily be plus or minus 20% off a value, off the actual value. We have a ways to go. We have to get better. That's another reason why I'm so excited to have so many young people in the audience, because I think we got a lot to cover. Typical approach is many AI models try to make very precise predictions, okay, regression type models, and for some kind of general system. And unfortunately, you need, I said millions, that's probably too high, hundreds of thousands of observations for this, and the results are actually not that accurate, plus or minus 20% easily. So let's talk about a classification approach. Okay, a different approach. What if we focused on grouping into performance? And I'm going to talk about fly ash specifically. And I'm just going to talk about, is it high? Is it medium? Is it not as good? That's it. Classification. Okay, and this is going to require a lot less data and still provide a crazy useful tool. Because if you talk to people today, people that are trying to buy fly ash, people trying to make decisions about fly ash, they would be just elated to know if something is high, medium, or low in like 5 seconds. And that's what these models can do. This requires a lot less data. It still provides useful tool. And what if we could do all of this with the bulk oxides? What are bulk oxides? I'm talking about that mill sheets that you get with the fly ash, right? Those are averages. You would want to know what it was for your specific material. Based off these bulk oxides, can we predict this performance? And we'll show you that you can. Kermit's excited. Are you guys excited? Yeah, we're excited, right? So basically, we're going to classify things into three groups. Class 1 would be less than Portland cement by 1 standard deviation. Class 2 would be the same performance as Portland cement. And Class 3 would be greater performance, Portland cement. Portland cement plus 1 standard deviation. So everything is going to be a comparison here. So we're going to compare, so it makes it easier to compare one fly ash to another. Basically, if you don't understand what I'm talking about, this would be Class 1 would be less than OPC, Class 2 would be about the same, and Class 3 would be a better performance. And I'm talking about data like this. Here is strength on the y-axis. Here is days after hydration or days of hydration. The black line there is Portland cement. And then we've got the red line is Class C ash and the green line is Class F ash. Now, you might say, well, okay, cool. I see these are the averages here. And you can see on average, Class C has an earlier strength than Class F, but longer term, they're about the same. But notice the spread. Notice how I have data points that are as high as the average, like easily 10, 15% higher than the average, and I have some that are lower than the average. So just calling them in a Class C ash, although that's what we do today, maybe we can do better than that. Calling them in Class F ash, maybe we can do better than that and better understand what's going on. And what I'm talking about is that if we looked at one of these data points, one of these points in time, breaking this into 3 different classes, Class 3, Class 2, and Class 1, based on the bulk oxide content. I'm going to use 30 traditional fly ashes and 14 harvested fly ashes. Now, how this model started out was only with traditional ashes. That was it. Then and it worked great. So we said, why not expand it to harvested ashes? And it works great. So we're like, this is awesome. Let's just keep going. So we have 22 Class C, 22 Class F ashes. These are tested at 20% replacement and 40% replacement, and we're going to compare them with a standard concrete mixture. And we're going to use a 0.45 water cement ratio, 6.6 sacks, which is a lot of binder, but we don't want to have any admixtures. Why? Because that may complicate things, okay? And we're not ready for that right now. We just want to understand how these fly ashes perform on a comparative basis. We're going to use 1 cement, we're expanding that, 1 coarse aggregate, 1 fine aggregate, but we're looking at all this information. Compressive strength from 3 days to 180 days. Resistivity from 3 to 180. Diffusion coefficient to 700 days, okay? And 48 hours of hydration. This is 2,655 measurements, that's a lot of measurements. And a lot of people that did the work are here in the audience. So big thanks to them and all their hard work. It's a lot of data that you can use. Now, we used 5 different machine learning models. And I'll tell you right up front, I have a partner at Oklahoma State University. He is in the electrical engineering group, and he has been doing machine learning for about 20 years, okay? So I've learned a ton from him. He has been a great collaborator on this, massive collaborator, and he can look at what he calls the fabric of the data, how the data is organized in space, and understand which ones will do well and which ones won't. He could just look at the data and know, oh, yeah, we need to try one like this, right? But we used 5 different models to say, okay, how does this one we chose compare to other ones using those 11 bulk oxides? And we're going to use one called, we're going to rank the models using called leave out X cross validation, or sometimes folks call it leave 1 out. So if X was 1, then I would say I have 44 training sets. So I'm going to use 43 of them to train, and I'll check it for that one. Then I'll leave out another one, then I'll leave out another one, and go all the way through, and I'll see how accurate is it. How accurate did it get myself in group 1, group 2, or group 3? Well, we didn't just use 1. We went all the way up to 8. So if you randomly choose 8 data sets out, right? Apply that. That's a lot of measurements, that's a lot of validation, that's a lot of looking. So what I'm talking about is this. Here are 5 models. Here's if I leave 1 out. Some of these did okay, but this one did really well, 94% accuracy. Okay? And over time, obviously, as you leave more out, you take more of the raw measurements out and test it more, it's not going to do as well, but it's still at 80% accuracy. It's not like it tanked to nothing. Does that make sense what I'm saying to everybody? right? That looks at the robustness of the model that you're actually looking at. So we called this the kernel PCA, and the first time I heard this, I thought he said Kermit. And so we call it Kermit PCA, right? After Kermit the Frog, right? Kermit PCA, it's kernel PCA analysis. Okay, that joke didn't go over well at all. But Nathan, I'm gonna keep trying, because why not, right? So we got to ask this question. Is this mixture, again, is it in class 1, is it in class 2 or class 3? I know there's a lot going on this slide, but here's compressive strength, 20% replacement, and here's how accurate we were, 98% accurate at 3 days. Okay, and we dropped down here, 89% accurate at 180 days. That's a long time to predict, 180 days. A lot of stuff can happen, 180 days. Still, on average, 94% accurate. If I go to 40% fly ash replacement, right, here's where I fall, still on average, 87% accurate. Let's look at diffusion coefficient, something that we really, really care about for durability, massive. Again, long average accuracy about 80% for both of these models. Pretty cool. Really, really, really cool. Let's talk about heat of hydration. If I'm trying to do mass concrete, make a decision about which fly ash to use, how much fly ash to use. This is powerful, useful to do. Okay, here's 83% accurate and 77% accurate. So this Kermit PCA or kernel PCA analysis is able to use its bulk oxides to group the performance of the fly ash. It groups, it looks into classification. Is it better? Is it about the same? Or is it worse? 20% replacement and also 40% replacement for 44 different fly ashes. On average, it's accurate 85% of the time. Gets it right in one of those 3 categories. That's pretty good. And that ranges between 94 and 77%, depending on what it is you're specifically looking at. So how can you implement this? This is the coolest part. You can take your bulk oxides and you type it into a website and you hit go. The website does all the calculations and compares how you did compared to OPC. And it's already live. And it's free. And it's ready. And you can use it now by going to tylerley.com/fly ash. My name, fly ash, on my website. It's pretty easy. Type in your oxide contents over here. It makes sure you're within the ranges that we've tested. So you can put in natural positive and be like, no, that doesn't apply. Okay, you hit calculate, and then it'll tell you, is it the same? Is it higher? Or is it lower? And the same means same as a performance of a mixture that only uses Portland cement. Is it lower? Is it higher? And why is this helpful? This is a way to compare, a way to adjust, a way to get a feel for where your material is versus some other material. So how in the world could you ever use this? This is a rapid screening tool, okay, that people are using now in practice to look at different materials, to understand how a fly ash source will impact your mixture design. You can look at blends of fly ash. So you have an on-spec fly ash and an off-spec fly ash. You have a C and you have an F. You have whatever, okay? Because of fly ash shortages, people have been using C's and F's in one concrete mixture. That wouldn't be something you would usually do, but they're doing it now. You can see how the blends perform. You can investigate fly ash that doesn't meet current specifications. Okay, you can build confidence in harvested fly ash. Now, I'm not sure people should need confidence because that stuff is awesome. Okay, I'll be talking about that on Tuesday afternoon. But if you get it to meet ASTM C618, it performs extremely well. So what would you do as information? This provides a much deeper insight than just class C versus class F. Uses 11 different oxides, okay? And we're entering a new era of fly ash. And we need new ways to understand what's truly going on with our materials. And so Kermit's excited, man. He's playing the banjo, eating some flies, totally pumped. And so why does this work? Well, the particle size distribution was pretty similar between all the materials that we looked at. If I use a very coarse ash, it doesn't perform exactly the same, okay? If I use a very fine ash, it doesn't perform exactly the same. But for ones that are traditionally on the market today in this range, it works really well. We've known chemical composition is important for a long time. The literature is riddled with documents that talk about all kinds of different elements and what they mean. This just goes in much deeper. Now we can take into all the oxides simultaneously. And actually, for most of these properties, you don't need all 11. You need about 4 or about 5 core oxides, and I'll talk about that coming up. And if you know what they are and what ranges they're in, you can make great predictions really quickly on how these things will actually perform. But you've maybe seen this ternary diagram before. Maybe if you're a fly ash person, maybe you've seen this plot, maybe you've seen class C versus class F. And this is a diagram that shows how much silicon, how much calcium, how much aluminum, and where different SCMs typically plot. And a lot of people have hypothesized that these are the main oxides that dictate or guide what's going on. We're building like an 11-dimensional figure here and looking at where these things fall and then where certain performances are for different criteria for different performance of that concrete mixture. So what's next? Well, we have an ASR model. It's done. I just don't have it out yet, and it's my fault. But, we'll get there. We've got 20 independent fly ashes. Okay, when you're already at 44, finding 20 new ones is kind of hard, all right? But we have 20 independent fly ashes that we've actually brought in to test. We're looking at cements with different alkali contents. And we also, this is probably the most exciting, we have a table-based method. I know I love websites too, but ASTM documents don't like websites, okay? They like tables, all right? Where you can go and look things up and go over and do stuff like that. To the young people in the room, you said, come on guys, grow up, all right? But to the people that use this stuff every day, tables are pretty powerful, okay? But we're building a table-based method where you basically look up 4 or 5 different elements, and we have these things called trigger points where you say, okay, if you're above this trigger point, you're an H. If you're in this category, you're an M. You're in this category, you're an L. You go into the table, you look some stuff up, and it will tell you which category you actually perform in. Again, high, medium, or low. All right, so in conclusion, machine learning tools are powerful. I mean, they are powerful, and that's one reason why it's such a packed audience today. Okay, and it will help us develop new understanding and insights into long-standing questions. And this kPCA model is able to accurately predict the performance of both traditional and harvested ash for compressive strength. I didn't show resistivity because I didn't think I'd have the time. Diffusion coefficient, heat of hydration, it is super powerful. If you didn't get that before, you can go to the free website, download it, use it, give us feedback. We've updated it probably like 6 or 7 times now. We've gotten user feedback, and we've got people that are regular users that use it all the time when they look at buying fly ash on the open market or how their fly ash is changing. And if you don't know anything about me, I've got a YouTube channel. You can find it at youtube.com/Tyler Relay. And if you are not a subscriber, please like, subscribe, leave me a comment, of course, and I will do my best to answer any questions. Thank you so much for being here. Take care, my concrete maniacs.
Hi, thank you very much for your great presentation. I want to talk about in point of view, the computer science, because I got my first PhD in the field of the computer science, and it's my second PhD that I'm studying on the civil engineering.
Yeah.
And with Professor Nani, the next president of the ACI. And I want to suggest something in your methods that, have you ever used the XGBoost linked with some meta-heuristic algorithms in your machine learning application or not?
No.
Okay. If you use, instead of the 94%, I think you can increase it to 98 and some cases to 100%. If you can do it, it will be great for your website and for your methods too.
Thank you so much for the suggestion. I'll check into it.
After the meeting, I will talk with you more.
That sounds awesome.
Thank you very much. Thank you.
Other questions?
I always get scared when anyone says 100%. You know what I mean? But that sounds awesome. I'm excited.
Hello.
Hey.
I'm Robin from Ghent University, and thanks for your nice presentation. I do believe machine learning is a powerful tool, but where there is a bit of an issue is that with machine learning, when they go outside their context of training.
Yes, for sure.
Are you concerned with that? And if so, how would you validate other mixtures with fly ash replacement out of such a context?
Good question. So one thing that I didn't show, but Robin, on each one of these, we have a range for each one of these oxide contents. We only restrict the model that we give out publicly to the range that's within this range, okay? So if you try a fly ash that for whatever reason has something else mixed into it, okay, that would throw it outside one of these ranges, then it would the model would, our model that's publicly available would stop. The model that we use would give you something that's probably illogical, but it depends how far outside actually it's unknown, but it's probably totally wrong. And I think that's one thing we have to be really careful about, is that these models will always give you an answer. An answer. I didn't say it was the right answer. It will always give you an answer. And that's why we have to check. That's why we have to refine. That's why we have to test. And that's why the quality of our data that we put in is so important, right? And I'm not saying anything that other people haven't said before, okay? Now, if you, I try to do everything as a relative comparison, because I'm trying to do a classification that's still useful to people, all right? If you used something that was very, very different, then you may get a very, very different answer.
Okay, thank you.
Hi,
Hey.
Laura Dalton, Duke University. So my question was, I think I only saw that there was one water to cementitious material ratio.
That's
so
right.
I was just curious if this is all based off of that one, how you think it might change the performance or anything.
That's a great question. So everything we did is based off one water cement ratio. We're trying to look at how fly ash impacts different properties. And we did it for one water cement ratio. And we're trying to do a relative comparison. And I would assume, and with the little work that we've done, and with the stuff we've done with people in industry, they've found that this is still very, very useful to them. So I would love to do more, but it's been a lot of money to get where we're at. But that's why we got young people in the audience, right? We're going to go further.
All right, thank you.
Hi, my name is Hossein from University of Illinois. Nice presentation. So I noticed like the data set is trained on 2,600 points, which is really great. And you share it like the link with all of us so we can go ahead. And so this is like something that is working. So my question is like, this is already trained on 40 fly ashes. And the next plan is to add up like another 20. So when is the time we can say, okay, that's enough? Like we have enough fly ashes, like this is like we have enough data set to confirm that our model is perfect.
Yeah, great question. Do you remember the leave one out cross-validation that I showed you before? Remember how I showed it where we used, oh, I went way too far, where we used, see how it's stable after 8? Mm-hmm. You want to run this, okay? And you want to see how fast it drops off, all right?
Okay.
And you want to push yourself to use a quarter to a third of your model is what we're trying to do. And you want to see how it responds after you've really hit it hard, if that makes any sense. And I think as you do that, you'll actually find things in your model that you're super sensitive to and other things that you're not as sensitive to. Mm-hmm. And that'll give you some idea where you need to add more data to make it more robust. Does that help?
Yeah, yeah.
So more data doesn't necessarily always help, but more data in the right location helps immensely. Mm-hmm. So you have to know where your weakness is,
Yeah.
so that you can add the right data in the right spot. Hope that helps.
Yeah. Awesome. Thank you.
Just a quick follow-up on that. Do you have any ways that, because you're looking at 11 kind of variables here, so are you able to quantify where those missing spots are? Because as you know, it's the interactions between these.
It is. So what happens is that when you start to do this leave one out cross-validation, it's leave X out or leave whatever out. As you start to pull out certain ones, all of a sudden you'll get an individual one that just won't fit. And you're like, whoa, why did that one have such a problem? And so you can go back and do some forensic analysis on that one data set and say, like, well, what was so sensitive about those choices? And then you can go back to your raw measurements and see which ones were actually taken out and say, okay, that means that type, that group is not as robust. So I need to add some more data in there. Does that make sense? Yeah.
Yeah, my name is Jun Wang from University of Colorado. Can I ask a question, like if you can make this program be an open source so everybody who have data can participate in, and let the model retrain so we can share the result together?
That'd be great. So I think she asked it. Yeah, I'm very open to open source. I think that would be awesome. I think that would be great. I think that one thing that I think is really powerful about my data is that all the measurements were done in my lab. Okay, and so I'm not as worried. I mean, and so I think some of them, there could be some things that are brought in that may bring in some variation, but I'm very open to that. I think that's something that we can work on and work on together, maybe. So if you got something that you want to share or whatever, let me know. I'm just running as hard as I can because I only got a limited amount of money, and as soon as I run out, I gotta stop till I can get people like Nathan give me more money, right? So I can keep on going. All right. So that'd be great.
Just a quick follow-up on the website, so people can use it. Can they input their data in there?
No, right now you just type in your Oxide content. This is very much an output. Yeah, you hit calculate, and it's actually more complicated than this now, but it spits this information out. Okay, but. And I've gotten feedback from industry, okay? I mean, we've partnered with industry. They've given us some feedback. There's been some good things about it. But I think you're right. I think putting data together and doing something more open source would be awesome. We just have to make sure that we really take care of the data that's in there. So we use Python to do a lot of our coding ourselves. We do some tweaks to some of the algorithms, and those are in the papers. All right, that have helped us get better. If you want to email me, I'm happy to share some of that stuff with you. Like I said, it's really great to work with a seasoned veteran in this. He's done a lot of this stuff, and so I've been learning a lot. So it's been good though.
Hi, Tyler. Great presentation.
Thanks.
Steve Tan, Heidelberg Materials. Is there going to be a next phase where you will look at admixture interactions?
I'd love to, man. I'm very open. This has been quite the journey, okay? And we'd be very open looking into anything. I think we have to make sure we go carefully forward, okay? Because if you just say, "I'm gonna give me all your data," then I think it'd be hard to know what's real and what's not. Okay, but I think if things are measured in the right way, or things are measured or done in the right way, I think that's very, very, very powerful. And my next steps, as I said before, the ASR model to get it out. We're adding 20 more fly ashes. Cement alkali content is what I was going to use a little bit of money on. Okay, and then this table method is something we're definitely. This is done for the most part. Okay, and the table method I think would be really, really powerful because now ASTM could have like a guide document, not a spec, but it would just give someone a guide information. But I think admixtures would be great.
Yeah, because I'm hearing things about increasing the accuracy of models, and then if we're not looking at critical variables. I mean, I've seen countless times in the industry where something happens at a fly ash plant, a burner, furnace is changed or what have you, and a cement lab does their testing, their bycats. Everything's within.
It's fine, and then you add a water reducer to it, and it goes to sleep.
The concrete is plastic for 72 hours.
Yeah,
admixtures weren't.
Yeah, no, it is. I totally agree with you. Some of the heat stuff that we did, you can see a little bit of insight with the sulfate depletion peak or whatever, a little bit, but you never know until you run it. And actually, for Illinois DOT, we did work where we did heat of hydration normal, then we had a heat of hydration with a water reducer, and we saw how much it delayed. Okay, and that was really powerful, but we don't have enough measurements yet. You know what I mean? We just don't have enough measurements to really let that out in the open, into the wild. I try to be really careful what I put out because I don't want people to kind of use something that they shouldn't.
Okay, awesome. Thanks.
Thanks for the question.